Hello, everyone, and thank you for joining us on this D-Zone webinar. My name is Jason Cockrum, and I'm the Community Engagement Manager here at D-Zone, and we're glad you've joined us. We've got a really relevant and an exciting topic for you today, and so we're happy that you're here. D-Zone is one of the world's largest online communities of software developers and experts, and we publish all sorts of knowledge resources for developers and really anyone passionate about software development. We've got things like ref cards and trend reports and thousands of articles written and published by our community. And all this makes us the go-to knowledge hub for developers all over the world. We also do a ton of great events like this one, and you can find them all at dzone.com/events. We've got things like fireside chats, virtual roundtables, and a bunch of other great stuff too. So be sure to check out dzone.com/events for all that information. Today, I'm joined by Dr. Christoph Dorn, who is the head of research at Vaticle. He joined Vaticle from Oxford University, where he was a theoretical computer scientist. So clearly he's much smarter than I am. And today he's going to spend a few minutes talking about type theory as the unifying foundation for modern databases. And as a theoretical scientist, there's probably not many people more qualified to talk about this. So without further ado, I'm going to hand things over to Christoph.
Thank you very much, Jason, for the lovely introduction. I'm excited to be here, and I'm going to talk today about some of the larger vision of what we're building at Vaticle, namely a unifying foundation for modern database application based on type theory. And just to let you know, this is only the first of 4 lectures. So this is the first lecture in our TypeDB Fundamentals lecture series. So if you like what you hear today, you should definitely attend the later events as well. To begin, I wanted to briefly recall the status quo of the database field today, and in particular highlight some of the issues that contemporary database languages are facing. Certainly, there are many different paradigms in use. We can work with relational databases, graph databases, document, triple zone RDF databases, and so on and so on. And we also take it somewhat for granted that these come with many commonly known problems. First and foremost, there's very frequent mismatches between conceptual level and logical level modeling. So that's a mismatch between how we conceptually organize our data and how we actually have to organize it in our database. Prominently, this includes the object relational mismatch, but also issues when working with reified relations, for instance, or multi-valued attributes, and so on. And this leads to unnecessarily complex code. So for instance, in this relational query, we're distributing the fields of a single object across many multiple tables. And the issue is really rooted in these existing paradigms lacking support for expressing very ubiquitous features in data, like data polymorphism, type polymorphism, but also interconnectedness and interdependencies in data. Second, we have the fact that none of these paradigms are built to enable easy system extensibility and maintainability. The queries that we write in them are often imperative and long and require us to supply hard-coded type information at several steps in these chains of imperative statements, which makes them very brittle and makes them very sensitive to changes in the underlying data layout. And the root cause here is that the existing paradigms don't natively provide facility for writing composable and generic queries instead that could be reused in a much more robust way. And then the third issue I want to highlight is data integrity. So in the absence of a sufficiently expressive schema, we just simply cannot express certain dependencies that our data might have. And then, of course, we also can't meaningfully validate those dependencies. That easily leads to a violation of the semantic data integrity. So for instance, in relational databases, we have no means to actually enforce that certain types of relations might only run between certain nodes. This causes us to easily create relations where actually it makes no sense to have relations in the first place. Similarly affects data redundancies, which often need to be manually and carefully updated to ensure integrity. This is just a very brief overview of some of the pain points, but it gives you a good idea of the type of issues we are trying to address with our fundamental work. If you want to hear more details about these problems, you should definitely attend our next lecture. So this is a plug for lecture number 2, where we need a polymorphic database by James. And today we'll take a slightly different route. We'll leave practice on the sideline and really focus on the more theory-driven journey that we're taking, with the goal being that hopefully you will understand the fundamental shift in paradigm that we're trying to achieve in our work. And that starts with the realization that existing paradigms are, of course, also built on theoretical foundations. For instance, domain-specific mathematical ideas like the theory of relations, the theory of graphs, of trees, and so on. And this means that they're very good at representing and at applying to domain-specific data, so data with a specific layout. But the moment your data goes beyond that layout, that blueprint, things get more complicated, as we've seen in the issues previously listed. There are many features in your data, like type polymorphisms, that cannot be natively expressed. And these paradigms are simply not built by design for the composability and extensibility needs of a modern system. And finally, it's also very little interoperability between all of these approaches to databases. So in our work, we really want to rethink foundations of modern databases from scratch, from first principles, to fundamentally improve the situation. And that, of course, needs to be rooted in theory. So that's what today's talk is about. So our database is rooted in somewhat modernization of many classical ideas, a general theory of composable structures, namely type-theoretic mathematics, and that will provide the inspiration for us to answer this question today. Jumping ahead a few steps, let me talk about TypeDB, which is the data based on the theoretical insights that I will talk about today. TypeDB is built at the intersection of classical databases and machine reasoning, and also contemporary type theory. And as such, it comes with a novel data model. So it's a data model that natively incorporates type polymorphism, and therefore we refer to it as a polymorphic data model. And it's not a relational graph or document database, but rather you should think of it as a unification of these ideas. It comes with a truly type-theoretic query language, something that we're going to see in this talk. So there's a close link between type-theoretic ideas and how we build our queries. And this goes hand in hand with the design of the type system that underlies querying the database, and is by design meant to be extensible hand in hand with the query language. And finally, there's a machine reasoning engine that allows you to integrate the application logic of your database application directly into the database. Again, that is powered by type theory. So all of these components of the database are powered by type theory. And in this lecture, we'll hopefully learn how that works. So let's start from the top. Let's start with talking a bit about type theory and how it modernizes mathematics. Let's start actually with the classical view on how data is organized and how mathematical structures are organized. So classically, we would think about mathematics as being based on two ingredients. On one hand, sets, and on the other hand, relations, also called predicates and governed by predicate logic, which you might have heard of. Let's make this a bit more tangible. So instead of an abstract set X, let's write the set of person. So P is an element in the set of person, and then a relation, for instance, could be a relation of marriages. So relation of marriage between P1 and P2 and the set of persons would tell you whether these two persons are married or not. So it would give you a truth value. And this type of classical mathematical thinking inspired, well, a lot of programming languages. It definitely provided inspiration for relational data, for relational databases, but it also inspired logic programming languages like Prolog, Datalog, etc. But as a matter of fact, it's very far from mathematical practice. So modeling everything in sets and relations is very restrictive and very cumbersome. So mathematicians nowadays usually have a somewhat allergic reaction to working with set theory. And in fact, mathematics has moved on. So mathematics has moved on to composable systems. So modern foundations are actually only based on one ingredient, and that's types. So the set of person is a type, and so is the predicate of marriages between them. So everything in a way is a type. And the type of marriage between two persons, P1 and P2, could have 0 marriages in it, or it could have 1 marriage instance, or even multiple marriages. So in this sense, it is an actual generalization of predicate logic. This approach of type 3 unifies all mathematical structures as types. Dependencies between these structures can be thought about as programs, and programs compose. So theory naturally has this composable flavor where you can take one program with an output type and feed it into a program with a corresponding input type. And this has been highly successfully applied, even in cutting-edge mathematics. So what we want to do here is we want to take inspiration from this very successful set of mathematical ideas. And just as relational algebra was based on 20th century mathematics dealing with sets and relations, we want to base modern database foundations on type theory. I'm not going to assume that that you're familiar with type theory in detail. So here's a very short crash course in type theory. It's not meant for mathematicians. It's actually meant for just English speakers. Let's start with the question, what precisely is a type? And I want to give the following definition. A type is a description of a domain that a variable can range over. So this is a very broad definition, and in particular, it applies both in mathematics and programming languages, but it also applies in natural language. So for example, in programming languages, we might have the type of integer, and saying x is an integer then describes the domain that x can range over as the integral numbers. Another all-time favorite is saying x is a string, y is a string, which then means that y can range over the domain of strings. But there are also slightly more interesting examples, like saying z is a factor of x. So this is more interesting because the description of the domain that z can range over now depends on a variable. So this would be called the dependent type. And for instance, if we set the variable x to 26, then z would range over the domain of factors of 26. So in this way, you can plug in actual variable values in a dependent type. Again, the definition is broad. It also applies to natural language. So just as saying x is an integer, we could be saying p is a person to describe a domain that a variable can range over. So p is a person says the variable p can range over the domain of persons. Similarly, n as the name of a person of p is a completely fine type, but a dependent type because it contains the variable p in the description. And as a final example, M, a marriage between P1 and P2, we've already seen that is also dependent type. And in general, there can be as many variable dependencies as you want. There's a lot more to type 3, of course, but importantly, a lot of it can be understood in natural language. So as we've just seen, dependent types, for instance, correspond to descriptions of a domain with a variable, but descriptions of domains, so types need not be considered in isolations. They can also be combined in various ways, and that's governed by type logic, generalizing predicate logic of predicates. So for instance, we could, as a first basic example, we could work with pair types. In natural language, this is simply combining descriptions with an and. So for instance, having a description x is a person and y is a city could be combined into a joint description x is a person and y is a city, using using the connector end. And this would then be a description of a joint domain for the pair of variables x and y. So this is why it's called a pair type. Another second simple example would be the sum type operator. In natural language, this corresponds to alternative descriptions with the connecting word or. So you could say, for instance, X is a person or X is a city. And that too is a type description. It constrains the domain of the variable X to be, well, the union of the domains of persons and city. In type theory, this is much more broadly generalized, and the key to this generalization is really dependent types. So, for instance, consider the following combined description: X is a person, and Y is a name of X. So this, at first glance, looks just as our pair type, just as our combined description that chains two descriptions with an end. But in this case, there's a dependency of the second description, so Y being a name of X on a variable that's described in the first part of the description, namely X is the person. And here we would talk about dependent pair types. And this brings me to the last important feature that we are going to need from type theory, which is dependencies compose. So let's consider a simple example here. We've seen all of these types already, so let's consider the type of persons with P1 and P2 being variables in the types. Consider the type of marriages of P1 and P2 with M being a marriage between P1 and P2, and then the type, let's say, of dates of M, with D being a variable that ranges over that type. Then these can be composed into a single combined type, which is a type of dates of marriages M of persons P1 and P2. So this would be a composition of these dependencies. And this is something that type theorists can actually formally write out. So here's how a type theorist would write it in a dependently typed programming language. So I'm picking Acta here, which is one of the most popular dependently typed programming languages. They could write sigma. Sigma is the symbol for dependent pair types, which we just met. They could write sigma P1 in person, P2 in person, M in marriage, P2, P1, and D in date of M. Now, looking at this, we definitely think that we can do better. So let's show the corresponding typeql pattern of this code. So typeql can also express precisely this dependent type. In typeql, you would write P1 is a person, P2 is a person, M of P1 and P2 is a marriage, M has date D. So this is a description of a domain that these variables can range over. So this is a type, it's a combined type. And if we now imagine that we fix a database, then this becomes a query. And this precisely describes the domain of data that you want from your database. And this brings us to the synthesis of databases in type theory. So let's just briefly recall what we've just seen. So we've seen on one hand, very abstract ideas from type theory, dependent types written in a somewhat obfuscated language can actually be understood in the context of databases as queries. So these combined dependent types can be understood as queries, and typeql actually lets you write this in a nice way. Reading out the one on the slide, for instance, the query on the slide, C1 is a city, C2 is a city, F from C1 to C2 is a flight, F has duration D, and D is less than 120. So it's a very intuitive syntax. But if it was really just for the dependent types, it would not be a practical query language. So dependent type theory is a very restrictive framework, and it serves well as a theoretical foundation for a database language, but a practical language cannot be as restrictive as type theory. So let's look at an example of how this plays out in practice. This is a variation of the previous query here. New York City, NYC is a city, has name New York. Dest is a city. F from NYC to Dest is a flight. F has duration less than 120, or you can think of 120 minutes. So again, intuitively, it's very clear what we want from our database. So the query semantics are very, very straightforward. But in practice, a user might not be able to specify or might not want to specify all the types in this query. So for instance, we could omit giving the type of our variable dest. We could even omit giving the type of our variable f. So maybe we don't only want to go to cities. Maybe we want to go to other places as well, which are not cities. And maybe we don't want to use just flights as our mode of transport. So removing these types still gives a valid type-kill query, but it begs the question, how can we actually interpret this? And this is where the second main component of our type-theoretic database comes into play. Namely, we need a type system that gives semantic context in which we can then do type inference and type validation for our queries. And might be a relief to some of our viewers that this is not formulated in the abstract language of type theory, but instead a core innovation of TypeDB here is that we instead work with an intuitive conceptual data model. So conceptual schemas are well studied, are a classical topic of database theory. But what's novel here is the interpretation of conceptual modeling in type theory. So let's see how this works. Let's start with the intuitive categorization of natural language that we usually assume in conceptual modeling. So this categorizes language into three categories. First of all, nouns. So for instance, a person is a noun, then verbs connecting nouns, a person marries another person, and finally, adjectives and adverbs, which quantify or qualify either nouns or verbs. So for instance, a person marries another person today. The conceptual modeler would abstract this and use the following terms and categories instead. They would say, well, the first category, these are entities. So for instance, the person is an entity. The second is relations. So for instance, a marriage between P1 and P2, that's a relation. And finally, we have attributes. The date of a marriage, that would be an attribute of that marriage. But we've already seen the close correspondence between natural language and type theory. So these three categories also make sense to consider in type theory. In type theory, an entity type is precisely a type without dependencies, whereas relations and attributes, these are types that describe things that have variables in their description. So they're types with dependencies, with the difference being that relations are somewhat abstract. They contain objects, which we refer to only by some pointer or some reference, whereas attributes are types that contain concrete values, like integers or strings. So in order to supply a database schema in TypeDB, you precisely take this type-theoretic conceptual perspective. So you specify your semantic information, your semantic context in which you run your queries in conceptual language, but interpreted from a type-theoretic perspective. Let's see how this works in action. Let's start from our earlier type-theoretic query. So just to recall this read, NYC city has name New York, F from NYC to Dest, F has duration less than 120. So let's go through this line by line and reverse engineer the entities types, the entity types, attribute types, and relation types that we need to provide the semantic context here. So the first line starts with NYC is a city. So certainly we need a city entity type. City doesn't depend on any variables, so it must be an entity type. It has name New York. So name must be an attribute type. But then we also must have names of cities. So maybe let me briefly add, it's an attribute type of value string. But in order to say that there are names of cities, we must specify that name can depend on city. So we do that by saying city owns name. Going to the next line, we need to provide context for the variable f. And one way to do this here would just be to specify an abstract type of transportation. But this now depends on variables. F depends on the variables NYC and dest here. So transport must be a relation type. And what are these from and to fields? Well, they mark the type dependencies. So they mark what transport depends on. So it's transport from and transport to that transport depends on. And in a way, they abstract these type dependencies in that, well, we specify that transport relates its from role and its to role. But in order for instance, a city like NYC to be able to play the role of having transport from it or having transport to it, we then need to specify that city can play this role explicitly. So this is semantic context that we provide. So we say city plays transport from and it plays transport to. And this is the context that you would need in order to run a query like this validly. Let's also look at the last line briefly. This says f has duration less than 120. So what this states is that duration is certainly an attribute. In this case, it has integer value long, and transport, so the type of f, must in particular be a type that duration can depend on. So there's duration of a specific form of transport. So we specify that by writing transport owns duration. And at this point, you see the two main components of type-DB in action. So you see the type-theoretic query language, the type-theoretic data retrieval language on one hand, which we understand now has elegant type-theoretic foundations. And on the other hand, you see in action the type-theoretic conceptual schema that provides the semantic context in order with which we can then interpret a query like the one on the left. Well, these are the first two theoretical components of the language. There's much more, and I want to briefly give an overview of what else there is. First of all, working type theoretically immediately gives us access to naturally incorporate type polymorphism into our models. And there are three common forms of polymorphism. The first and most common one is inheritance polymorphism. Inheritance polymorphism lets types inherit the specification of a parent type, and that enables us to organize our semantic context and our schema or type system in a hierarchical way. Let's see an example of this. This is a snippet of our earlier schema. So it defines the name attribute, the city entity type. It also defines transport, and it says that city plays the role of having transport from it and having transport to it. Now, what we can do is we can also define a specialized form of transport. So we could say flight sub transport. And simply by writing flight sub transport, flight will inherit the full specification of transport. It will inherit that transport depends on from and to dependencies. And it may also inherit, for instance, that transports have duration. But then we can give further specialized semantic information about flights. So we might, for instance, specify that flight has a flight number, where flight number is an attribute of value string. So in this way, we can very cleanly organize our schema into inheritance hierarchy. The second type of polymorphism is interface polymorphism. Interface polymorphism abstracts the input types in dependencies. And actually, we've seen this one already in multiple forms, in multiple shapes and forms. So interface polymorphism allows us to, instead of specifying precise input types, so instead of, for instance, saying that only cities have names, we instead work with the capabilities of having a name. So we abstract the capability of having a name and then allow other types to implement that interface, that capability. So here's an example, again, starting from our earlier schema, which defines the attribute name and then says that city is an entity type which owns name. But there could be other entity types and other types in general that also own names. So for instance, person could be an entity type that also owns name. And by adding this line, we now allow the name of type to not only have name of cities, but also name of persons in it. So both city and person share the capability of having names. This also affects the dependencies of relation types. So we've earlier seen in our example of the transport relation that city was, for instance, a type that plays the role of having transport from it and it plays the role of having transport to it. But there could be other types, again, that also have these capabilities. For instance, we could define the type of airports, sub-entities, so an entity type of airports, which also plays the role of having transport from it and having transport to it, independently of the city entity type. And this would provide then context to interpret our earlier query. For instance, destinations in our query, what we can reach with transport in less than 2 hours from New York. Destinations could not only be cities, they could also be airports or really whatever place you can think of. The final type of polymorphism I want to mention in the trinity of polymorphisms is parametric polymorphism. So parametric polymorphism defines generic functionality for variabilized types, so actually without knowing the type. And this, for us, enables the ability to write semantically fully generic queries. So here's a simple example. We could write a query as follows. So this is now not just a pattern, so not just a type if you want, or a description of a pattern. It's a deletion query. And what it does is it matches anything, any type that owns name, any object in something. So something owns name, object is a something, object has name, and if it finds anything of this generic form, it will delete object from the type something. So queries of this form, this is a very simplified example, are semantically generic. They're completely agnostic to changes in the underlying schema when it comes to, for instance, ownership of names. There's a final important component which I promised you. So this is reasoning, which is also natively a consequence of working in type-theoretic foundations. So the sigma types, the dependent pair types that we saw, is only one half of type 3. The other half of dependent type 3 are pi types, and these generalize implications. So implications from classical and predicate logic, as you're used to. And we use these form of dependent types or dependent functions to express the logic of our database, to express how some data can be inferred from other data. And in TypeDB, this gives rise to the concept of rules. Again, it's not trivial to make rules work. Let's look at an example here. This is a rule named possible two-leg flight, and it reads as follows. When flight 1 from C1 to C2 is a flight, has arrival time 1. Flight 2 from C2 to C3 is a flight, has departure time 2, and time 2 is greater than time 1 plus 30, then there is a two-leg connection with leg 1 being flight 1 and leg 2 being flight 2. So this gives a refined way of inferring data, inferring new data from source data in your database, and it uses the same syntax, the same type theoretic syntax that we've already seen in our data retrieval queries. So in particular, it's very intuitive to use. What this rule does should be pretty self-evident and self-explanatory. However, to really make it work, you need to build a reasoning engine. You need to build a efficient reasoning engine that evaluates these rules at query times, ensuring your data is always fresh, nothing needs to be pre-computed, and so on and so on. And this talk is not going to be about the details of the reasoning engine, which is certainly its own talk, but I do want to point out that it gives you very fine-grained control over your application logic, and you can encode a lot of application logic directly in the database. And this is in fact a feature that we see in very restricted forms in other databases as well. So it's a more general way to look at features that you also have in other databases. So for instance, in relational databases, you have views generated from tables, and in graph databases, you work with paths, which are generated from nodes and relationships between these nodes. And in document databases, you might work with aggregates based on the collections that you have. This brings us to the last point, to the last part of our talk, which is the unification of existing database paradigms. So we set out to build a modern database that could handle a variety of data structures, and that makes it very easy to write semantically valid code that is easily extensible, and that in particular generalizes what's already there. So this type-theoretic approach is more general. This type-theoretic conceptual approach is more general than the existing paradigms. And let's briefly illustrate this on this slide. For example, if you compare to relational databases, then there's a very clear translation, almost one-to-one translation of how you would migrate. Tables in a relational database are, at a first look, they're simply entity types. Even though at a more refined look, you might find that associative entities are better modeled as relations. But actually, this type of semantic context is not provided by a relational schema. So without further semantic context, you cannot tell whether an entity is actually an associative entity, which is also known as a join table, by the way. Foreign keys become relations between these entities, and columns with a value become attributes of entities. So here's a simple example of an easy relational database, but modeled with the type-theoretic conceptual schema of type DB. So table student with two columns, maybe the subject of study of the student and the start date of the student, could simply be modeled as an entity type that owns the corresponding two attributes. We add to this a table of professors, 3 columns. Maybe there's a name for the professor, the number of students the professor has, and maybe some Boolean attribute, whether the professor is taking new PhD students or not. And then we also have a foreign key that maybe assigns to each student their supervisor, and that can then be modeled with a relation. So a relation that precisely relates supervisee with their supervisor. There's a similar one-to-one correspondence for other data models. Let's briefly look at the graph model, where node types correspond to entity types, edge types naturally correspond to relation types, properties of either edges or nodes can be understood using attributes, and path composition is precisely the application logic that you're interested in. So the way your relations compose to other relations. However, in contrast to the type-theoretic approach, the graph database has usually very little control over the logic of how composition happens. So in our example earlier, for instance, with 2-leg compositions, we saw that we could very easily build in a minimum a buffer of 30 minutes between 2 connecting flights. And something like this would usually be not as easy in graph databases. So let's also look at an example. Let's look at a graph which first has, let's say, city nodes. So you model city as an entity type. Maybe these nodes are named. So they would own a name attribute. And then there can be flight edges between these cities, which, well, relate the departure city where the flight is departing and the arrival city where the flight is arriving. And they also own attributes themselves, like departure time and arrival time. And then on top of that, you could specify the context, the schema for the logic that you're interested in. So for instance, a simple example that we saw earlier was the two-leg flight example, where you would combine two flights with sufficient overlay time into a two-leg flight. But of course, the possibilities are infinite here. And very similarly, you can model other database paradigms, document, RDF, and more in type-2B very naturally, precisely because in its conception by design, we start at the conceptual level of data modeling. So I hope you enjoyed this very fast overview. If I were to summarize the two main takeaways, I would say that on one hand, you should take away that type theory certainly is abstract, but it's something that we almost use on an everyday basis. Like when we model concepts depend on one another. So it's very natural to take dependent type theory actually as a starting point, as an inspiration to design a journalistic modern database. And then secondly, that there's a lot of power from providing semantic context. So from having an expressive schema language that can in particular avoid issues of data integrity violation and many mistakes that engineers are not even aware that they're making. If you want to learn more, please attend our next lectures. This was just a very broad overview and a somewhat abstract overview of what is to come. But we're going to bring things even more down to earth. We're going to tell you more about the details of TypeQL, of TypeDB in the upcoming lectures.
Thank you so much, Christoph. We appreciate you sharing your insights with us today. That was very insightful. And a very special thank you to everyone who tuned in. Don't forget to check out our website, dzone.com/events, for a ton of other great stuff, just like what you've seen here. Thank you so much, everyone. We really appreciate you joining us, and we'll see you next time.